Pleasure of introducing Xinhe Meng from Nankai University, who's going to be talking about Finslerian cosmology and H0 tension. Yeah, please take it away.
Good day, everybody. I don't know your local time, maybe in the morning, maybe in the afternoon, maybe at night. Anyway, so it's my pleasure to give a talk in the international so special situation. Actually, this conference organized in 2019. At that time, Yang Hui stayed at Nankai. We discussed, we have a conference like this. But unfortunately, in the 2020, we have the special situation. So now we have a chance to talk with each other on the internet. It's also very interesting. So today I introduce a kind of a new model based on Finslerian geometry. So first, I'll give a kind of motivation why I established a model based on Finslerian geometry instead of Riemann geometry. Then I'll give some kind of specific example, the model building for the based on the a special case of Finslerian geometry. After that, we'll confronting with data and some diagnostic judgment with two parameters. We call it the acceleration parameter and the Okama brother parameter, the so-called. Then we extended the model with some dark radiation, so-called still neutrino. We'll see the results. The last is the discussion and some conclusion. So why I chopper my size, starting with the Finslerian geometry, not the relatively easier Riemann geometry. The reason is mainly due to the recent cosmic observation, the so-called H0 tension. Roughly speaking, H0 tension is two group of observation. One from CMB, the typical value is from the Planck 2018 results. And another group is from the race group in Berkeley, in Johns Hopkins. For the same parameter, the fundamental parameter in the cosmology, Hubble constant, they got two different values. One is a little bit bigger, around 17.4, another around 67. This in the compare with the standard model in particle physics, this is a sharp tension. The deviation reached about 4.7 sigma. So how to do it? Actually, there are a lot of trying. Some put a kind of so-called dark radiation or early dark energy or modified gravity, etc. Maybe 100 models. But in this talk, we are focused on the geometry. That is the following we introduced. So this is the actual tension, just as I mentioned. The two local group, they got the value around 6.7, and other groups, especially based on the CMB observation, they got larger values. So that tension is acceptable for a so-called standard cosmology model. But we try to relieve this tension. So what is the Finslerian geometry? I'll give a very simple introduction. So first, you have a Finslerian form which should satisfy the following three properties: regularity, positive homogeneity, and strong convexity. So this is a requirement for the Finsler form. With this kind of form, you can define a matrix with the Finsler form. Then similarly, like the Riemann geometry treatment, you can get a torsion-free and almost compactable connection. The meaning is the following. So the first term is a crystal form, just like a Riemann geometry, same. So the duration from the Riemann geometry is by the big C, this so-called Cardan tensor, which means if the Cardan tensor is 0, then this geometry is reduced to Riemann geometry. So in this sense, Finsler geometry is an extension of Riemann geometry. So in this kind of setting, we have a special type named renders space, which means you have a special Finsler form. By this kind of form, we name this kind of Finsler geometry renders, which is a simplified Finsler geometry. So big A just by I should have mentioned small y is the coordinate in the manifold. So and the little a mu is just the Riemann geometry metric. So you can use it to raise and lower the index, just like we usually do in the Riemann geometry. So with this kind of mathematical setting, we can even to simplify the form with the render space to take it as a very special assumption with the little b just with time component non-zero. This kind of render space named for another type. So far we start from a general Finsler geometry. Then we take a special case, which means render space. In render space, we specify the connection. This guy with this requirement. So this type of render space is called Burnett type. Actually, it's a very simple Finsler geometry. So with this setting, we can conveniently to parameterize the additional contribution with the two parameters. One's alpha, another is beta. You can have a look. Alpha is mainly the time component, and the beta is the space component. So we have two additional parameters. So with this mathematical structure, we can rewrite the action, the gravity action. So this action is encoded with the two more parameters, alpha, beta. Then with this action, we do the derivation. We got the main equation for the contents of the universe. If you use the ideal fluid with the particles. So this is the density of the matter. And the alpha beta, just I mentioned, is just the two additional parameters from a Finsler geometry, from a special Finsler geometry, wild type Finsler geometry. So in this sense, if we assume the contents, the matter contents in the words satisfy this kind of equation state. Similarly, you can get the density scaling way like this. If you have a careful look, you can find when alpha and beta equals 0, it reduces to the Warnow-Friedman case. So the dynamic equation for the universe, the Hubble law, read like this. This is for the curvature 0 case. In recent 2 years, a lot of cosmic observation indicate the data prefer curvature non-zero. So if you put curvature, include the curvature in the dynamic equation, you got additional term, curvature term. So we name equation 7 simply is just the Finslerian lambda model. It's a simple extension model. And equation 8 is non-flat Finslerian lambda model. We just give a name. So far we have the modified cosmic dynamic evolution, the 2 models, equation 7 and equation 8. So the next question is that reasonable? How we can charge is reasonable? So we confront with the observation data. We say how the model works. So next is quite direct. If you use the Monte Carlo MCMC calculation, you can check the model. This is the first model, the Finslerian with the flight Finslerian model, the curvature 0 model. This is the main parameter, matter, equation state, the 2 new parameter, alpha and beta. This is the likelihood. You know the chi-square, minimum chi-square, you got the likelihood value of the parameters. So we can compare this model with the 6th parameter, the lambda CDM model. We can say its derivation or its additional contribution, how much of additional contribution. So in 2 sigma, it's compatible each other. So we got the confidence. This model, it's not unreasonable. It's okay. we do the similar for the non-flight Finslerian model. Equation 8. Equation 7 is the flight case. Equation 8 is non-flight. We find the H value in this model is around 70. It's just between the 2 groups. One group says it's about 67, around 67. Another is 74. So we got the value is between the 2 values. In this sense, we say we relieve the tension. We relieve the H0 tension. Maybe I know this community a lot of working on quite a formal theory, but maybe not so familiar with a lot of data feeding. So I take a briefly introduction. So the first 3 is just from the Planck result. The first is the so-called the optical types. It's an observation by the Planck, 2018. So this value is we put. It's coverage. We give a prior from negative to around the 0, from negative to positive. Alpha beta is just the additional 2 new parameter in the extended model. And the H0 is the target we want to release. So this is the MC programming working in this program. So you can see the 3, 4, 6. This is the standard lambda CDM model. So what we did, we extended the model with 2 new parameters. So this is our story. The results, just we mentioned, it really released the tension about the H0. You can see this one, a little bit relieved. H tension is too sharp in today's observation. Besides H tension, actually, we have the sigma 8 tension and the omega m and the age, the universal age tension. So for reasonable model, you only account for 1 is not enough. A nature question, can you explain other tensions? So we extended the model. This is I just in the introduction I mentioned. Besides the data conferencing, you can also have use the accelerating and omega radar parameter to check, cross-check. This region is in the 2000 region with the lambda CDF, which means it's a compatible model. Also with the Okama radar parameter. So just we mentioned, actual tension we should relieve. How about the other tensions like the sigma 8 or the universal age and the matter contents? So we extended the model in the Finslerian geometry based model. We added dual neutrino contents, the large N effective. This is new parameter. Also, we can, so this is altogether is nine parameter. Also, we not only the generation number, we also compute stellar neutrino mass as a fitting parameter. So equation 9, this is a 10 parameter extended model based on the previous Finslerian models. So this is our continuous story. We want to not only accounting for the H0 tension, but also the sigma 8 and the omega m and the universe age. I should speed up, time flying. So we just do the MC, and we got the parameter. The sigma 8 is a little bit relieved compared to the new tension. This is just the fitting plot. I'll just skip up. Okay. So this is age and mass diagram. So with the, if actually people have some kind of idea, we need a new ingredients, so named dark radiation. A physical realization of the dark radiation from the standard model of particle physics is quite naturally is stellar neutrino. So how massive for the stellar neutrino can realize to relieve the tension, the age and the mass. By the MCMC, we find if the stellar mass less than 0.1 EV, it's EV, then the tension can be relieved. So this is the result. Also, we can find the H0 in the extended model, the best value. I should quickly do. So this is the first part based on the Finslerian geometry. Just I mentioned, we have two kind of work. One is based on Finslerian geometry, another is a cosmic back reaction model. We model the back reaction effect with the three form. So far, I don't know if there are some questions for the Finslerian. If no, I will continue for the last part for this kind of model. So generally, for the cosmic back reaction, we can write the action like this. This is a GR, and this one is just a back reaction. So laterally, people also use the back reaction as the source of dark energy. As we know, GR is a classical theory, so we don't know the right hand of the matter contents. Are there some perturbation contribution or some quantum effects? So generally speaking, we can attribute this contribution with the back reaction. So how to model the back reaction? The question is, we extended the framework as a general back reaction form with two new parameters. I should mention, in this case, alpha beta is not the previous Finslerian alpha beta. Is that's the model extension. It's kind of a parameterization. If alpha equals 0, so this back reaction model reduces the previous one. So the following is similar. We use the observation from a cosmic to constrain the extension parameter. So this is a SAMB, and this is the BAO, the spiral earthquake oscillation data, and with the sound horizon size. This is also observation from cosmology. You can public get the data from the plan. So we use data analysis and do the chi-square check. So this is too technical. I should be speed up. This is the data from the spiral acoustic oscillation. So far with different redshift and different size. In a easy understanding language, it's kind of a large yardstick to measure the universe. You just can understand with this way. So we put all this together, we got the final result. we can see clearly for the extended model, alpha, beta not goes to 0, the result is better. So the tension can be released from 4.7 to 2 sigma. I didn't say I can resolve the problem. I just say we can relieve the tension. So far, this is the main result. The following is a discussion about the form of back reaction. Actually, this part is a kind of quite phenomenology. We write the GR equation with a kind of fluid. We got the volume average for the back reaction effect. I should say frankly, so far there's no standard way to get the back reaction and formulas. Also, it's quite complicated to do the volume averagation. So far, we just analogically can have the back reaction term. This is just similarly as the Friedman equation. So with this formalism, we can have a belief the three-form back reaction term is reasonable. So I should give a conclusion. So far I talked two parts. One is based on Finslerian geometry. We use a very specific Finslerian geometry to extend the so-called 6-parameter cosmology model and relieve the Xinhe tension. And second part, we use the back reaction effect to discuss sigma H or Xinhe extension. And the result is to just relieve the tension from around 4 sigma to sigma. But the underlying reason why the tension is still an open question. So thank you, everybody. I think I have several minutes for questions.
Thank you very much, Xinhe. That was really lovely. Yes, as I said, if that's probably a good opportunity to open the floor. If anybody has any questions, please unmute yourselves and go ahead.
I have just noticed a friend, Hai Tang, is online.
Yeah, 孟老师
你好，你好。
你好，你好。I'm the next speaker.
I see.